Hello everyone, welcome to the channel. This is the third video of a three-part series, mean value theorems and beyond. In this video, we will be solving some more problems on mean value theorems. So let's start with our problems. You can pause and try these problems before watching the solution. So now let's read the first question. It says let f from 0, 1 to r be a twice differentiable function such that f of 0 is equal to f of 1 is equal to 0. Suppose the minimum value of f of x in this interval is -1. Then we need to prove that the maximum of the double derivative of x in this interval is greater than or equal to 8. So my first thought when I saw this problem is to use Taylor theorem, because we don't have any information about the first derivative. Yeah, so let's see how we can apply Taylor theorem here. So we are given that minimum value of f of x is -1. Let's say for some b belongs to 0, 1, f of b is equal to -1. Now what I'll do is I'll apply Taylor theorem twice. Once in 0, b and the other time in b, 1. I can write f of x is equal to f of b plus f dash of b into x minus b by 1 factorial plus f double dash of c by 2 factorial times x minus b whole square, where c belongs from b to x. Yeah, now I'll break this into two intervals, which is 0, b and b, 1. When I substitute x equal to 0, we are given that f of 0 is 0. We get 0 is equal to, and f of b is -1. And from Fermat theorem, we can say that the slope of tangent at the extreme point will be 0. So I can neglect this term and write 0. And this is f double dash of, call this c1 by 2 times b square, where c1 belongs from 0, b. Now if I rearrange the terms, I'll get that f double dash of c1 is equal to 2 by b squared. Now similarly, if I do the same process in the interval b to 1 and I substitute x equal to 1, I get, we are given that even f of 1 is 0. 0 is equal to f of b is -1 plus the single derivative term vanishes plus f double dash of, let's call this constant c2, divided by 2 times 1 minus b whole square. Now if I again rearrange the terms, I get f double dash of c2 is equal to 2 by 1 minus b whole square. Now I'll write the both results at a single place so we can see something. F double dash of c1 is equal to 2 by b square, and f double dash of c2 is equal to 2 by 1 minus b whole square, where c1 belongs from 0, b, c2 belongs from b, 1. Now let's take cases. Let case 1 is if b is less than or equal to 1 by 2. If b is less than or equal to 1 by 2, I can see that f double dash of c1 is greater than or equal to 8. Now the other case will be if b is greater than or equal to 1 by 2, which means that if double dash of C2 is greater than or equal to 8. So you can see that in either of the cases, no matter what the value of b is, either of the double derivatives is greater than or equal to 8. So from this, we can say that the maximum of the double derivative in this closed interval 0 comma 1 will always be greater than or equal to 8, which is what we were to prove. I hope everyone understood. Now let us move on to our next question. Our next question says, let f comma g from closed interval a comma b to r be continuous on closed interval a comma b and differentiable on open interval a comma b. Suppose f of a is equal to g of a, f of b is equal to g of b. We need to prove that there exists at least one c belonging to a comma b such that f dash of c plus f of c into g dash of c is equal to g dash of c plus g of c into f dash of c. It is also provided that f of x and g of x is not equal to 1 for all x in this domain. So now, in order to proceed with this problem, let us analyze the result and then make ourselves an auxiliary function and then apply Rolle's theorem to get our answer. So let me arrange the terms. What I'll do is I'll combine these two terms and take out a g dash of c common. I'll combine these two terms and get an f dash of c common. What I'll be getting is f dash of c into 1 minus g of c is equal to g dash of c into 1 minus f of c. 1 minus f of c. Now what I'll do is I'll take this term to the denominator and this term to this denominator. I'll get f dash of c by 1 minus f of c minus g dash of c by 1 minus g of c is equal to 0. So now we can see what our function will be. I'll take h of x is equal to f dash of x divided by 1 minus f of x minus g dash of x divided by 1 minus g of x. Now my goal is to prove that this h of x will have at least one root in 0 to 1 so that I can get my result. Now in order to prove that this will have a root, I'll use Rolle's theorem. Now you can see that this is nothing but d by dx of ln of 1 minus f of x provided a minus, and even this is negative times d by dx of ln of 1 minus g of x. Now I'll take the function p of x is equal to ln of 1 minus g of x by 1 minus f of x. We can see that if I take the derivative of p of x, I'll get h of x. Now what is p of a? P of a is nothing but 1 minus g of a by 1 minus f of a. Numerator and denominator will be equal since f of a is equal to g of a. And I'll get ln of 1, which is 0. Similarly, when I substitute b, I'll get p of b also 0. Now since p of a and p of b both are 0, I can apply Rolle's theorem and say that there exists C belonging to A comma B such that P dash of C is equal to 0. But we know that P dash of X is equal to H of X, which means that H of C is equal to 0, which is what we were trying to get. Now, since we got H of C equal to 0, we got this result, which in result will again give us this, which will give us the given equation. This is how we approach this problem. I hope everyone understood. Now let's move on to our next question. Our next question says, let P of X be a polynomial with real coefficients whose roots are all real and distinct. We need to prove that if Q of X is equal to this expression, then Q of X will have no real root. Now what we'll do is, let us consider P of X is equal to an x power n plus an minus 1 x power n minus 1, so until a1x plus a0, where all these coefficients are real. Now what I'll do is, I'll use factor theorem and I'll write this as a9 times x minus r1 x minus r2, so until x minus rn, where r1, r2 till rn are the roots of P of X. Now what I'll be doing is, I'll be considering this equation and I'll try to change it into a format that we can understand. Now seeing the RHS, we can say that it's something like of the form quotient rule. But in quotient rule, we have some whole square term in the denominator. So let's see with what should we divide so that we can get a whole square term in the denominator. Here we can see that it is P dash of X into P dash, I'll write it up. P of X is equal to d by dx of P of X times P dash of X minus P of X into d by dx of P dash of X. Now in order to make this in the form of quotient rule, we need to divide by P dash of X whole square. But what I'll do is, I'll multiply with a minus on both sides and then divide by P of X whole square. Because I have some information regarding P of X which is its all roots are real and distinct. But I don't know anything about the single derivative. So I'll proceed in this way. And now we can write LHS, which is minus Q of X by P of X whole square is equal to d by dx of P dash of X divided by P of X. Now let's see what will be our P dash of X by P of X. We took P of X is equal to an times x minus r1 times x minus r2 till x minus rn. Now what I'll do is I'll take natural log on both sides. I'll get ln of P of X is equal to ln of, in multiplication since the logarithm breaks, I can write as ln of an plus ln of x minus r1 plus so until ln of x minus rn. Now I'll differentiate both sides with respect to x. I'll get P dash of X by P of X is equal to summation I equal to 1 to n 1 by x minus Ri. Now in this equation we have d by dx of p dash of x by p of x. So let's differentiate this equation again with respect to x, which gives us d by dx of p dash of x by p of x is equal to minus times sigma I equal to 1 to n 1 by x minus Ra whole square. Now I'll substitute this in our expression. Minus q of x by p of x whole square is equal to minus summation I equal to 1 to n 1 by x minus Ra whole square. This minus will cancel, and now I will see that we can see that this term is always a greater than 0 quantity, and also p of x whole square is also a greater than 0 quantity, provided we are not substituting any of these Ra's, which will make our equation undefined. To keep our equation defined, we don't substitute the roots of p of x, which will give us that p of x whole square is a strictly greater than 0 quantity, and this summation is also strictly greater than 0 quantity, which will imply that u of x is also strictly greater than 0 quantity, which means that it will never cross the x-axis in the whole real domain, which proves us that q of x doesn't have any real root in the real domain. I hope everyone understood. Now let's move on to our next question. This is, let f from 0 comma 1 to r be a continuous function such that f of 0 is equal to f of 1 is equal to 0. Suppose that for every pair of points x comma y belonging to 0 comma 1 with absolute value of x minus y less than or equal to 1 by 2026, mod of f of x minus f of y is less than or equal to mod of x minus y's whole square. We need to prove that f of x is strictly 0 for all x belongs to 0 comma 1 in the closed interval. Now our question says that this property is valid only for x and y that satisfy this condition. Now in this question what we'll do is we'll take the geometric meaning of modulus, which in modulus we nothing but distance. Modulus of x minus y is nothing but the distance between the points x and y. Now let's see how we tackle this problem. What we'll do is let the graph go from 0 to 1. I will take some arbitrary point x in between 0 and 1. Now what I'll do is, in between this 0 and x, I'll break this interval into n equal segments. Like I'll call this x1 and I'll call this next one x2 and so on till this segment is xn minus 1. Now let's call 0 as x0 and x is equal to xn for our convenience. Now what is this is, I divided this into n equal parts and the length of this whole interval is x. So if I divided this into equal parts, the length of each segment will be x by n. Now if I need to proceed, I'll make sure that this x by n is always less than or equal to 1 by 2026. Now what I'll do is, now if I take f of x minus f of 0, I can write it as summation I equal to 1 to n f of xi minus f of xi minus 1. I'll also write x naught is equal to 0 and xn is equal to x. Now this is nothing but an obvious statement. Now what I'll do is, I'll take modulus on both sides. Now if I apply triangle inequality for this modulus, I can take the summation sign out, I equal to 1 to n, and I will put the modulus inside, f of xi minus f of xi minus 1. Now since the difference between each xi and xi minus 1 is less than or equal to 1 by 2026, we can use this property. Now I'll apply this property and I'll get mod of f of x minus f of 0 is less than or equal to summation I equal to 1 to n mod of xi minus xi minus 1 whole square. Now since we divide this whole interval into equal segments, xi minus 1 is nothing but x by n. Now what I have is x by n whole square times summation I equal to 1 to n of 1 itself, which will give me x square by n. Now from here I can say that mod f of x minus f of 0 is less than or equal to x square by n, and it is always anyways greater than or equal to 0. Now what I'll do is, if I tend n to infinity, x by n will tend to 0, which is less than 1 by 2026. So a property will hold true. So I can limit n to infinity, which will give me that if n tends to infinity, 0 is less than or equal to mod f of x minus f of 0 is less than or equal to 0. From here we can say that f of x is equal to f of 0. If we weren't given that f of 0 is equal to 0, our answer would be that f of x is a constant function. But since we are given f of 0 is 0, we can say that f of x is equal to 0 for all x belonging to 0 comma 1. I hope everyone understood. And here we were also given f of 1 is equal to 0. It was not any use, but it would be confusing for us in the examination, so we need to take care. Now let's move on to our next question. You can do this problem again on your own to understand. Our next question is an ISI 2023 UGB question. It says, let f from 0 comma 1 to r be a continuous function on closed interval 0 comma 1 and differentiable on open interval 0 comma 1. And we are given that suppose f is non-linear. We need to prove that there always exists t belonging to open interval 0 comma 1 such that mod f of 1 minus f of 0 is less than mod f dash of t. We are given that f is non-linear, which means that f of x is not of the form ax plus b. Now what we'll do is, we'll take an arbitrary point k belonging to 0, 1 and then apply LMVT. Now if I apply LMVT in the interval 0 to k, I'll write that f of k minus f of 0 divided by k is equal to f dash of c1, where c1 belongs from 0 to k. And if I apply in this interval f of 1 minus f of k divided by 1 minus k is equal to f dash of c2, where c2 belongs from k to 1. Now what I'll do is, I'll send this k to the other side and this 1 minus k term to the other side. And I'll get that f of k minus f of 0 is equal to k times f dash of c1, and f of 1 minus f of k is equal to 1 minus k times f dash of c2. Now what I'll do is, I'll add these both equations and we can see that f of k will be cancelled and I'll get f of 1 minus f of 0 is equal to k times f dash of c1 plus 1 minus k times f dash of c2. Now I'll take an mod on both sides and then I'll apply triangle inequality on this to isolate these terms. I'll get mod f of 1 minus f of 0 is less than or equal to mod of k times f dash of c1 plus mod of 1 minus k times f dash of c2. Now since k is a greater than 0 quantity, we can take it out of the modulus sign and we'll have this expression less than or equal to k times mod f dash of c1 plus 1 minus k times mod f dash of c2. Now since f is not a linear function, if we compare f dash of c1 and f dash of c2, surely we can say that one of them should dominate the other. Without loss of generality, let's say that f dash of c1 is greater than f dash of c2. Now you can say that maybe in some interval f dash of c1 may be equal to f dash of c2. But since k is a moving point in 0 to 1, we cannot guarantee equality in every case, because if we guarantee equality in every case, it will mean that function is a linear function, which our question says is not possible. So in some for some of the other k, f dash of c1 will be greater than f dash of c2. Now if I apply this inequality to this, I'll get that mod f of 1 minus f of 0 is less than or equal to k times mod f dash of c1 plus 1 minus k times mod f dash of c2, which is less than mod f dash of c1 times k plus 1 minus k. The k will get cancelled and we'll be left with less than f dash of c1. Now what we'll do is we'll call c1 equal to t and we'll get that mod of f of 1 minus f of 0 is less than mod f dash of t. Now since c1 belongs from 0 to k, this means that this will belong to 0 comma 1, means this is a subset to 0 comma 1, which means t will also belong to 0 comma 1. Now this is what we were asked to prove, that mod of f of 1 minus f of 0 is strictly less than mod f dash of t for some t belonging to 0 comma 1. I hope everyone understood. So this is the end of our video and we'll be starting a fresh topic in our next video. I hope everyone understood. Thank you. Take care. Goodbye.